This is a toy universe. It's just a row of squares, each one blue or black. As time moves forward, the universe evolves down the page, and at every step in time, the colors get updated according to a certain rule. The color that a square becomes next only depends on the colors of itself and its left and right neighbors in a specific way that I'll write out in a minute. The rule is called Rule 30, and it functions as the fundamental law of physics in this universe, completely determining its behavior. These are the first 32 steps it generates, at the very beginning of the universe. If we let time keep running forward, we start to see new features that weren't obvious before. On the left, there's a lot of order. There are these striking diagonal structures that repeat over and over again. So something relatively simple is going on here. The rest of the picture looks complicated though. It's hard to see much structure. Small black triangles appear throughout, but they don't follow any apparent pattern. Except on the far right boundary. In this thin sliver, the triangles seem to be spaced regularly. So something simple is going on here too. In this video, we'll discover why the left and right sides of this universe behave like they do. They'll tell us quite a bit about Rule 30 as a fundamental law of physics, specifically about whether we can run it backward in time as well as forward. This is work I did in the very first research paper I wrote, about 20 years ago. Okay, so what is Rule 30 actually? Here it is. What this says is there are 8 cases. Whenever we see blue, 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 we get a black square on the next step. That's what happens right here, for example. We have 3 consecutive blue squares, and the middle one turns black. Whenever we see blue, blue, black, we get a black square, and so on. That's all of physics in this universe. It's extremely simple. Why is it called Rule 30? Well, there's a natural way to encode the rule by interpreting the blue and black squares as 1s and 0s. This sequence of 1s and 0s is the binary representation of some number. The 4 1s are in the 2's place, the 4's place, the 8's place, and the 16's place. So add them up, and you guessed it. This universe that Rule 30 generates is an example of a cellular automaton. The cells are the squares, and an automaton is just a self-running machine. Rule 30 was discovered by Stephen Wolfram in 1983 as part of a systematic study of cellular automata. If you consider all rules of its type, where there are 2 colors and the color of each square depends on 3 squares on the previous step, there are 256 of them. To give you a sense of what they look like, here are the first half. I should say that I'm starting all of these from a single blue square on a black background, although of course you could use other configurations for the initial state. Most are pretty boring. Simple lines or stripes or other repeating patterns. Some of them generate self-similar patterns, like Rule 90 here. But even for those, it's fairly easy to work out the general behavior. There are just a handful that are doing something complex, generating arrays where it's not obvious what's about to happen next. Rule 30 is one of them, and it resists attempts to work out its general behavior. It's like the digit expansion of pi. You can compute it all day long, but you don't see a pattern. Take the center column, for example. There are basic questions about it that we can't answer. Does it end up in a repeating cycle? Probably not, but no one knows how to prove it. Is the distribution of blue versus black squares exactly half and half? Again, this seems to be the case, but we don't know how to prove it. And is it possible to compute it more quickly than the cellular automaton does? If there's structure in the center column, we should be able to determine the color of, say, the trillionth square without running the whole automaton a trillion steps. But we don't know about any such structure. Even though it's created by a simple rule, it's statistically random as far as anyone can tell. By the way, each of these questions is worth $10,000 if you can answer it. $30,000 for all 3. So why is this picture so complicated? It's hard to say. The behavior of the automaton is an emergent property of the rule. Knowing what's happening on one level doesn't really tell you what's happening on the next level up. But some aspects of the behavior can be traced directly back to the rule. The right boundary. Why are there black triangles in this array at all? Take this triangle. The top row is a block of 8 consecutive black squares. These are bookended by blue squares. Let's follow the rule from here. Since 3 consecutive black squares produce a black square on the next step, a long block of black squares will produce another block of black squares, just possibly shorter. In fact, that's exactly what's happening in what we think of as the background. a long block of black squares stays black. What about the two endpoints of the top row of the triangle? On the left, blue, black, black becomes blue, so the block of black squares shrank by 1 on the left. And on the right, black, black, blue also becomes blue, so the block also shrank by 1 on the right. Over the next several steps, the block gets smaller and smaller until it disappears. So that's one triangle. Further down along the right boundary, we see a bigger triangle. It's formed in the same way, kicked off by a block of 14 black squares. And if we keep going, here's another triangle. Its width is 8. And this one has width 15. If we keep going even more, the next widths are 8, 14, 8, and 23. Will we keep getting bigger and bigger triangles? Next, we get 8, 14, 8, 15, 8, 14, 8, 24. This sequence of triangle widths seems to have some structure. For example, at the first appearance of 15, what came before? 8, 14, 8. And that's exactly what we get next, 8, 14, 8. Then we get a new number, 23. And after that, we get a copy of everything leading up to the 23. And then another new number. So whenever a new number appears for the first time, what happens next seems to be a repetition of the entire sequence we've seen up till that point. It's a beautiful structure. Actually, you may have noticed that we skipped a bunch of smaller triangles on the right boundary, so we should really fill those in. Here's the top of a width 6 triangle. Here are 2 5s. These are little 3s that only last 2 steps before disappearing. And in this context, it makes sense to call these blocks width 2 triangles, and they're just too narrow for the triangle to span more than one row. This sequence of numbers includes the previous sequence, but is more natural, since now we're capturing information from a lot more rows. Actually, every other row. But you know what would be even more natural? Capturing some information about every row. And there's a great candidate for this, if we ask about where the triangles themselves are coming from. Just above each block of black squares that begins a triangle is a block of blue squares that kicks off the block of black squares. And indeed, blue, blue, blue goes to black. These blue blocks are 1 longer than the black blocks they produce. If we focus on them and their lengths, now on every row we can record the length of the rightmost block of blue squares. All the lengths we don't have yet turn out to be 1s. So starting at the initial state, the lengths of the blue blocks are 1, 3, 1, 4, 1, 3, 1, 6, 1, 3, 1, 4, 1, 3, 1, 7, and so on. This sequence still has the same repetition structure. So to completely describe it, and thereby predict the behavior on the right boundary, we would just need to identify the new number that appears after every repetition. The new numbers are 1, then 3, then 4, 6, 7, 9, and we can get more terms by computing more rows. To try to see a pattern, we should get as many as we can. And the nice thing is we don't have to compute the whole array to do it. If we want to know the colors of these 10 squares, we only need to look at the squares that can possibly affect them. That's these 12 on the previous step, and these 14 on the step before that. Tracking this light cone backward in time to the initial state, we find all the squares that can possibly have an effect. Most of them are part of the background, which stays black, so we don't need to bother computing them. That leaves just these squares. So these 10 squares in the initial state determine the 10 squares we're interested in. And in fact, they determine the rightmost 10 diagonals of the entire automaton. Using that fact, I was able to compute these additional terms, and my code took 14 months to run that far out. In the process of making this video, I found out that just last year, someone computed 4 more terms in just a few days, using code that's extremely efficient. These are due to Miles Wilson, and the amount of computation here is ridiculous. It required running Rule 30 down to the 2 to the 46th row. That's 70 trillion rows. And computing the rightmost 128 diagonals in each row, overall, that's 9 quadrillion bits. So, do you see the pattern? Yeah, me either. No one knows a fast way to compute these numbers. So forget the center column. We can't even tell what's happening 130 squares from the boundary. But even if we can't predict these numbers in advance, we should still be able to see why the sequence we extracted them from, the lengths of the rightmost blue blocks, has the repetition structure we saw. So why is that? When we see 1, 3, 1 at the beginning, why must we see a repetition of 1, 3, 1 almost immediately after? It's related to the fact that the diagonals are periodic. This is easier to see if we shear the array so that the diagonals are rendered as columns. The boundary diagonal is blue on every step. These two diagonals repeat every 2 steps, and this diagonal repeats every 4 steps. In particular, these rightmost 4 diagonals as a group repeat every 4 steps. On the first 3 rows, these diagonals completely determine the block lengths, because we see a black square after 1 blue square, after 3, and after 1. So 4 steps later, these block lengths repeat. But on the 4th row, we don't see a black square yet, so all we know is that the block length is at least 4. Here it turns out to be exactly 4, but the next diagonal to the left hasn't necessarily started repeating yet. So 4 steps later, we may see something different. And in fact, we do. This is how new numbers appear in the sequence of block lengths. And where they appear is determined by the period lengths of the diagonals. The next diagonal repeats every 8 steps. This one also repeats every 8 steps, then 16, and then 32, although there aren't enough rows on the screen to see 2 full periods. The period lengths seem to be powers of 2. That would explain the repetitive structure in the block lengths. A new number can only appear at a power of 2. And after that new number appears, we get a repetition of all the block lengths we've seen up to that point. Great! But why are the diagonals periodic in the first place? And why are the period lengths powers of 2? Let's look at how the diagonals are constructed, because this is where the details of the rule come into play. Since we've sheared the automaton, let's shear the 8 cases to match. Every diagonal receives information from 3 diagonals, itself and the previous 2. The reason the boundary diagonal is blue on every step is that everything to its right is black, and blue, black, black goes to blue. The next diagonal receives information from itself, the blue boundary, and the black background. So the only piece that can change is the color in the diagonal itself. There are 2 possible colors. They both happen to occur, and once one of them occurs for the second time, everything that follows repeats as well. That's a pretty simple example, but the same idea works for every diagonal. There are only finitely many different states that a group of 3 diagonals can have. So at some point, one of those states must show up a second time. If the previous 2 diagonals are periodic, then from that point on, the third diagonal proceeds exactly in the same way as it did the first time. That explains why every diagonal enters a repeating cycle eventually. But why are they periodic from the start? There's a special property of Rule 30, and that is if we flip the color of the left input square in any of the 8 cases, it flips the color of the output. For example, take blue, blue, blue. It outputs black. But if we flip the left square, we're in this case, black, blue, blue, which outputs blue. These 2 cases differ in their left square, and they differ in their output. The same is true for this pair, blue, blue, black, and black, blue, black, different outputs. Also true for blue, black, blue, and black, black, blue, different outputs. And for blue, black, black, and black, 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 again, different outputs. Actually, you can see this just by looking at the outputs. Flipping these 4 outputs gives you exactly these 4 outputs. This property is called left permutivity, because each pair of cases corresponds to a permutation of the 2 colors, blue and black. Let's think about what this means for the automaton. What happens if we take a square in the initial state and flip its color? Ignore everything to the left and just focus on its diagonal. That flip causes the square directly below it to also flip. And that flip causes the square below it to flip. And so on in a cascade reaction, completely predictably all the way down the diagonal. In other words, the information in the initial state has a long-term effect on its diagonal, because if we flip the color of a square, it changes every square below it. So the information about the color of a square in the initial state is preserved on every subsequent row. That information isn't lost. And this is a really cool property, because if information isn't lost, then there's nothing special about the direction of time. If information is preserved going forward in time, then it's also preserved going backward in time. If we wanted to force a different color of a square down here, we would have to flip the square up here. So we can flip our whole argument around in time and conclude that from any row, each diagonal is eventually periodic going up the page in addition to going down the page. That's why the diagonals don't just enter repeating cycles eventually, they start repeating from the very first row. We'll get back to why the period lengths are powers of 2 in a minute, but first I have to tell you my favorite consequence of the diagonals being periodic. If we're tracking periodicity up the automaton, why stop at the first row? Just keep going periodically backward in time. And not just this diagonal, we can continue all diagonals backward in time. This gives a history of the universe before the initial state. So does that mean that as a fundamental law of physics, Rule 30 is reversible in time? In other words, is the history unique? Well, not quite. All the diagonal periodicity we've been talking about traces back to the black background. And we made an implicit assumption that the background diagonals are periodic. Under that assumption, yes, the history is unique. But the black background doesn't need to stay black as we move backward in time, because a block of black squares doesn't necessarily come from another block of black squares. It can also come from a block of blue squares. So an alternate history looks like this instead. But let's go back to assuming the background stays black, because there's one more amazing conclusion to draw. If we undo the shear, we see what the history looks like in the original layout. And because we can, let's run it backward in time a little further. Now, imagine we hadn't said anything about running Rule 30 backward in time. What would you say this is a picture of? This looks like a huge but finite black triangle. And the amazing thing is, we can't tell the difference locally. Because when we run Rule 30 forward in time, eventually we'll see exactly this picture. Periodicity of the diagonals means that certain rows have to look more and more like the initial state. Since the initial state has infinitely many black squares to the left of the single blue square, the black triangles along the right boundary do actually get bigger and bigger. So this picture of the initial state along with some of the history appears again way down along the boundary every time we get to a sufficiently big triangle. In fact, all the black triangles along the right boundary are mini recapitulations of the initial state. Here, Rule 30 is starting again inside itself. This is what I call local nested structure. And it implies that every finite region that appears reappears infinitely many times, and not only in the future, but also in the past. Before we wrap up our exploration of the right boundary, let's finally figure out why the period lengths of the diagonals are powers of 2. It also comes from the left permutivity of the rule, and the reason is quite nice. Suppose 2 consecutive diagonals as a group repeat every 2 to the n steps for some n. We'll see that the period length of the next diagonal divides 2 to the n plus 1. Since the only numbers that divide a power of 2 are powers of 2, this will give us what we want. Periodicity is about certain squares being the same color. Let's look at 3 specific squares in that diagonal. The top square, the square 2 to the n steps later, and the square 2 to the n steps after that, which is 2 to the n plus 1 steps down from the top square. These 3 squares can't be 3 different colors because the only options are blue and black. So 2 of them have to be the same color. If it's the first and the second, then at the second square, the diagonal will behave just like it behaved from the beginning, so the period length divides 2 to the n. If it's the first and the third, then at the third square, the diagonal will behave just like it behaved from the beginning, so the period length divides 2 to the n plus 1. And if it's the second and third, then the diagonal behaves the same at those 2 steps, so the period length divides 2 to the n, and since we can continue upward periodically, in fact the first square also has the same color as the second and third. So either way, the period length divides 2 to the n plus 1. So along the right boundary, the diagonals are periodic, with period lengths that are powers of 2. The reason this doesn't stand out visually when we look at the array is that the period lengths just grow too quickly for our eyes to be able to pick up the structure. But on the other side, it's a different story. The left half. On the left, visually it's clear that the diagonals enter repeating cycles. But they're not actually periodic from the start. We can see this better by rendering these diagonals as columns. The repetition doesn't start at the initial state. And this means that information down these diagonals can be lost, because if it were preserved, then the repeating cycles would continue backward in time all the way up to the initial state. So flipping a square in the initial state may not have a long-term effect on its diagonal. Let's see what happens when we flip the square just to the right of the initial blue square from black to blue. Did you catch it? Now I'm toggling that square back and forth, and you can barely tell a difference. Not only does it not affect its own diagonal, it hardly affects the rest of the automaton. Only at the right boundary is there any difference. But of course, there are lots more possibilities for the initial state. Some of them do have more dramatic effects on the right half. But the left half is pretty unfazed. The structures shift up and down, but they appear to be completely unchanged otherwise. So aside from these shifts, does any information from the initial state actually have a long-term effect on the left half? Or is there essentially just one left half of Rule 30? Let's extract the eventual repeating cycle from each diagonal, because we'll see a pattern if we look at where the period lengths change. The boundary diagonal is solid blue. The next diagonal, also eventually blue. Then we get an eventually black diagonal, then alternating between black and blue. So here the period length increased. Then back to solid blue. Then two more alternating. Solid black. And now a longer cycle with length 4. Then solid blue. Then a bunch with length 4. One alternating. Some more 4s. Solid black. And then a longer one with length 8. Then back to a blue diagonal. And a bunch of 8s. If we look at the first appearances of 2, 4, and 8, we can actually tell what causes the period lengths to increase there. Interestingly, they're sandwiched on both sides by solid color diagonals. The previous diagonal is solid black, and the next diagonal is solid blue. We'll work through the first appearance of 8 to see why the previous diagonal must be black. There's also a nice explanation for why the next diagonal is blue, but I'll leave this to you to work out for yourself if you want. Some extra copies of the previous 2 cycles will help us see how they affect the diagonal we're interested in. Let's bring up the rule one last time, and shear the 8 cases to match. We're only going to need these 4 cases, where the middle input square is black, since the middle of the 3 diagonals is solid black. And there's something special about these 4 cases. In the first pair, the left input square is blue in both cases, so the inputs only differ in the right square. And what do the outputs do? If the right square is blue, then the output is black. If the right square is black, then the output is blue. So in both cases, the diagonal flips its color from one step to the next. That's what we see at the top here. The left and middle squares are blue-black, so the right diagonal flips from black to blue. Same on the next step. Again, the previous 2 diagonals are blue-black, so the right diagonal flips again. But now the left square is black, so we need to look at the second pair. Again, the 2 inputs only differ in the right square. If the right square is blue, the output is blue. If the right square is black, the output is black. In both cases, the diagonal keeps the same color from one step to the next. So in our computation, the right diagonal keeps its color and stays black. Now the left square is blue again, so we flip. At this point, we've gone through the entire cycle of the 2 previous diagonals, because remember, as a group, they repeat every 4 steps. But in the right diagonal, we haven't returned to where we started yet. The right diagonal began as black, but now it's blue. And why? Because the number of times it flipped its color is odd. 1 flip for each blue square in the left diagonal. So over the next 4 steps, it'll flip again an odd number of times. And then we'll be back to where we started. So when there's a solid black diagonal, the period length doubles precisely when the diagonal to its left has an odd number of blue squares in its cycle. What about if we don't have a solid black diagonal? Well, if we see a blue square in the middle diagonal, then we're in one of the other 4 cases. In this pair, again, the 2 inputs only differ in the right square. But look what happens. The outputs are the same. So here the automaton loses information about what was in that right diagonal. Since both outputs are black, we can't recover whether the previous square was blue or black. And in this pair, the outputs are also the same, both blue. So the automaton loses information here too. Middle blue squares are bad for reversibility in these diagonals. If a repeating cycle contains even a single blue square, it causes the next diagonal to its right to forget all information about itself. And this means that its repeating cycle only depends on the cycles of the previous two diagonals, and therefore can't possibly be longer than those cycles. That's why the first appearances of 2, 4, and 8 occur right after black diagonals. Anywhere else, and the period length couldn't increase from the previous two. Okay, so does this tell us whether there's only one left half of Rule 30, completely independent of the initial state? If we're gonna see some variation, then at the very least, information in the initial state needs to have a long-term effect on some diagonal. We just saw that the only place information is preserved is to the right of a black diagonal. So that's our only hope. But is that enough? We know the period length can double there. And if it doubles, the second half of the new repeating cycle is a flipped copy of the first half. So the entire cycle doesn't actually carry any information about the initial state, because either way, we would see those same two halves. But must it double? At the first appearance of 8, the period length doubled because of an odd number of blue squares in this cycle. If there had been an even number of blue squares instead, then the period length wouldn't have doubled, and there's a possibility that information from the initial state would determine which of the two possible cycles we get. So we're looking for a solid black diagonal with an even number of blue squares in the cycle to its left. But instances of this turn out to be hard to find. The good news is that we don't need to search naively through initial states. We can work directly with the cycles themselves, using each consecutive pair to determine the possibilities for the next cycle. It takes almost 400 more diagonals to get to another black cycle. In the cycle before it, the number of blue squares is 3. Since 3 is an odd number, no luck there. The period length doubles, and we get the first appearance of 16. After that, we don't get another black cycle until diagonal 53,208. How many blue squares are in the previous cycle? 6! An even number! So instead of the period length doubling, it'll stay at 16. And there are two possibilities for what happens next. If the top square in the next cycle is black, then the trajectory of cycles continues like this. But if the top square is blue, then it continues like this instead. And if you keep computing these trajectories, thousands of diagonals later, you see more black cycles. And in fact, these are also both preceded by even numbers of blue squares. So they branch out into 2 more possibilities. After that, in 3 of the 4 branches, the period lengths double. But the 4th branches again. And presumably this branching keeps occurring, so that conceivably there are infinitely many different possibilities for the left half of Rule 30. Now, do initial states exist that actually give rise to any of these other possibilities? I don't know. But my guess is that yes, they do exist. And if that's the case, then it's pretty nice, because it means that even though the left half is extremely regular, it's still performing an interesting computation. Rule 30 isn't the only cellular automaton rule with left permutivity. I put together a bonus video showing several others, like this one. It's free to watch on Patreon. And if you'd like to support videos like this, consider becoming a member. Thanks so much for watching.